Wenqi, and in this part, I will be introducing the adversarial attacks for recommendations. Let's get started from a toy example in image domain. As we all know, deep neural networks are vulnerable to adversarial attack. Here, we have a picture of panda S, which is correctly classified as pandas by a classic deep neural networks like the CNN model. However, if we add some small adversarial noise, the assumes to be checked. Although to us human, this is still a panda, but the neural network is fooled and classifies the picture as the given with high confidence. Here, we want to show that the deep models can be attacked and manipulated with malicious desire from the adversaries by modifying the data. Similarly, despite the great development of deep recommendation models, adversarial attacks can also happen in most existing recommender systems. For example, it's reported that the e-commerce platforms like Amazon and eBay, or the social media platforms like Facebook or Twitter are flooded with fake reviews or connectives. And these fake reviews are really damaging to shoppers or business alike. And millions of people made their shopping decisions based on the reviewers. So if these are misleading or untrue, then the shoppers can end up being misled into buying something that isn't right for them. However, in research community, we haven't explored this adversarial attack problem a lot. And the work of them to defend against this potential attack is to understand how attacks can be performed. This is the major motivation of this section. And one of the most popular ways to attack recommender systems is the data poisoning attacks or shilling attacks, where attack aims to generate users with well-designed profiles to promote or depromote target items in recommender systems, so as to manipulate users' decisions. For example, to attack the target item, VJ here, with the promotion probe, an attacker can create fake user profile with a set of items and inject them into the training dataset. Then the recommender systems may use the normal dataset and the fake data to make the prediction. Here, the attack aims to manipulate the recommender system results so as to have the target item recommended to as many users as possible. And according to adversarials, different and the adversarial attack can be grouped according to different criteria. For example, according to the adversarial's knowledge, we can have the white box attack, gray box attack, and the black box attacks. In the white box attack, an attacker can get all the information of the target systems and use it to attack the system. This information can be the training data sets, the gradient information, the model architecture, and parameters, etc. And in gray box attack, an attacker gets unlimited information to attack the systems. For example, an attacker may only note the training data sets, but have no idea about the target model, like the model parameters and architecture. Actually, with the privacy and security issues and the concerns in recommender systems, It's impossible and unrealistic to expect this kind of knowledge. So we have a black box attacks where the attacker doesn't know any knowledge about the target models and the data set. And what the attacker can do only is to perform the black box queries. In addition, we can have targeted attack or the non-targeted attack, where attackers aims to attack specific items, while the non-target attack focus on the overall recommendation performance. In this tutorial, due to time limitation, we will introduce some representative attacking methods in recommender systems based on how much information of the target systems the attacker can access. First, let's look at the white box attack. This paper is data portioning attacks on factorization based collaborative filtering, which was proposed in NIPS 2016. And let's start with some background in this work. This work aims to attack the widely used recommendation methods, the matrix factorization. And given these user item interaction M with the observable interaction, user I and the item J, the goal of this collaborative filter is to recover the matrix M from the few observation interactions. And to solve this problem, alternating minimizations can be applied to learn the user and the item representations with some recognized terms. This is a very basic recommendation methods. Next, we describe the data portioning attack in this paper. In this work, they assume the attacker can access the full knowledge of the recommender systems. And under the white box attack, such as the overall training data set and the gradient information and the model. So for data matrix consisting of M users and N items, the attacker aims to add another some malicious user and filtered to the training data matrix. Then this the formulation of the training objective will be add one more turns on the malicious users. It's also to discover the malicious user data. The goal of attacker is to find optimal malicious user M tutor start so as to manipulate the recommendation results as much as possible, like the maximize the errors of the collaborative filtering systems, or the boost and reduce the probabilities of specific item. At last, they propose to use the projective gradient ascent methods to solve the optimization problem and learn the optimal delta start. Next, we will introduce representative attacking methods under the gray box attacks, where attacker gets limited information on target items, target systems. The revisiting adversarial learned injection attacks against the recommender systems. This work was published in RecSys 2020. In this work, they first assumes the attacker can fully or partially access the training data set only, which is used to train the target recommendation model. And so with this training data sets, the attacker is able to change their own surrogate recommendation model. And the attacker will use this surrogate model to help generate some fake users by attacking their old surrogate model. In this case, it can be treated as the white box attack. And the next step, the attacker will ingest these fake users into the training data sets of the target model. And after the target model computes these poisoning data sets, the attacker can achieve the initial goal. In this work, the goal of attacker is to promote certain items. And how to learn these fake user profiles. In this work, they formulate the attacking methods as a bi-level optimization problem. They will attack their own local surrogate model first. To do this, they will let the surrogate model train on scratch with the poison data first. Here, the normal data is denoted as X, and the S hat is denoted as the injected fake users. They use L-trains to denote the training objectives of the surrogate model. It can be the mean square errors for the L-train. And they optimize the L-trains to get the surrogate model, the optimal parameter, the theta star here. And after they get this star at the optimal parameter of the current surrogate model, they can produce the recommendation results on the normal users. And the adversarial objective is actually defined on the predictions for the normal users, because we want to have attack actually affects the normal users, the recommendation list, right? Here, the adversarial objective, which is ADV, can be the software cross entropy loss, which labeled as the target item. As we can see that there are two optimization problems which are associated with the theta star here. That's why we call it the bi-level optimization. And we want to use these by optimization methods to attack, to solve the attacking problem. To efficiently solve this bi-level optimization problem, this attacker use the gradient-based approach to get the fake user profile. So in the gradient-based method, they first change the surrogate based on surrogate model based on the fake data and the normal data. And then they obtain the gradient, which is adversarial loss regarding the fake data, and use this gradient to update the fake data. And they repeat these procedures until the adversarial loss get to converge. And actually, the challenge here is how to compute this disease gradient. By applying the change rule, the exact adversarial gradient can be revised in this form. And the first part assumes the S is independent to other variables, right? And while the second part suggests star can also be a function containing X. Actually, this fake data is involved in computing the adversarial loss. However, in most existing work, they lack exactness in gradient computation, as they assume the final parameter of the surrogate model star is independent from the fake data, but it's obviously incorrect. Let's look deeper in the computational graph for this optimization. The solid black arrow denotes the forward computation flow, and the dashed red arrow denotes the gradient back propagation flow. Here, the theta yellow is the initialized value of the surrogate model, and then they use the prediction and the normal and fake data to compute the surrogate model partialness gradient, and they then perform the update according to the optimizer here. They do this again and again and again for optimizing the inner objective until they reach the final final theta L, which is ultimate parameter of the surrogate model. As we can see, as then they compute the normal data prediction and evaluate the adversarial loss. As we can see from this computation graph, the fake data is involved in the computation computing the adversarial loss, which means we can actually compute this gradient we want. So to do this, once we define this computational graph, we should mutate this graph and then use the automatic differentiation to compute the desired gradient. It can be easily implemented as we have very friendly deep learning libraries like the TensorFlow and PyTorch. We can use it just do the backpropagation and get the gradients on the fake data as head. And last, we will introduce a representative attacking methods under the breadboard setting. The CopyAttack, attacking the breadboard recommendations via the copying cross-domain user profiles. It published in IJCAI' 2021. First, existing attacking methods aims to generate fake user profiles, right? However, these generated fake users are easy to be detected since they may present very different patterns from the real users' profiles. So, how to inject these fake users with profiles similar to the real users is still a key challenge, which may limit the ability to perform successful attacks on the deep recommender systems. On the other hand, some real-world recommendation platforms have similar functionalities. For example, product recommendation platforms, Taobao and JD.com. They can share a lot of items, right? And the Amazon and Best Buy have millions of products in common. Moreover, users in these platforms with similar functionalities also share similar behavior patterns and the user's preferences, which is well known as the cross-domain recommendation. So to tackle the first challenge in existing attacking methods, in this work, instead of generating users with fake profiles, we propose to copy the cross-domain users with real profiles from other domains. Here is an example. We have a target domain A and the source domain B for the movie recommendations. These two domains share a set of movies. So to attack the target item VJ here, the user profile U and B in the source domain B can be copied into the target domain A as a new user, such that the movie J is attacked as adversarial desired. In fact, it can be the case that there exists two e-commerce platforms in competitions with each other, right? One platforms can attack the recommendation performance of its competitors, such as the competition between the Taobao and the JD.com, Amazon, and the Best Buy. And the second challenge we might meet is the majority of existing attacking methods. They may focus on the white box or the gray box settings, where the attacker can acquire to have full knowledge of the target model or the training data set. However, with the privacy and security concerns, expecting such kind of knowledge is impossible and unrealistic. Therefore, this work proposes a reinforcement learning-based black box attacking method that learns to choose the user profiles in the source domain, which only query feedback from the target recommender systems. Now let's take a look at the whole framework. There are three main components: the user profile selections, and the user profile crafting, and injection attack, and the query. The first component is to perform the user profile selection for a specific target item from the source domain B. To adjust the challenging of effectiveness and efficiently in RL, we develop a hierarchical structure policy gradient networks with the masking mechanism to effectively learn the strategy of efficiently selecting the cross-domain user profiles in a large-scale discrete action space. Next, we're selecting a cross-domain user profile. The second component is used to do the profile crafting. Here, the profile crafting aims to further modify the user profile by considering the reduction of attacking cost and noise. Let's detail the first component. User profile selection aims to learn the strategy of selecting the cross-domain user profiles, as most existing IL techniques cannot handle in such a large-scale action space. To address this challenging, we introduce a hierarchical structure policy gradient network to model the process of selecting a user profile. More specifically, they construct a hierarchical tree over the cross-domain user profile, where its leaf node is represented as a user profile, and its non-leaf node is a policy gradient network. So we can see selecting a user profile in this hierarchical clustering tree is to fix a path from the rule to a certain leaf of the tree. Moreover, to further reduce the action space, we introduce a masking mechanism to locate the informative cross-domain user profile, where we mask the cross-domain user profile. They do not include the target items. So with these methods and strategies, we can significantly reduce the time complexities of making decisions in RL. And the selecting cross-domain user profiles contains informative signals regarding the target item. It's true, right? However, it's not necessary that all the interactions the core cross-domain user has are helpful. So just naively injecting the entire user profile into the target recommender systems may not only increase the attacking budget, but could increase some noise as well. Therefore, it's desirable to craft or refine the selecting cross-domain user profile before the injection attack. Yeah, we connect the cross-domain user profile with a window size W around the target item. More specific, we also build a policy gradient network to choose the action W from the sets W to decide the length we should keep. Actually, there are two main reasons. First, as the user behaviors towards items contains sequential patterns. The forward backwards interactive items around the target items are more related to the target items than others. Second, the sequential orders users' interactions are close to real user behaviors. So they are more likely to erase the detection from the target system. At last, the last component, we have the classified cross-domain user profile, and it is copied into the target systems for attacking the model. And queries by the spy users on the target recommender systems are performed to get some feedback in the form of the top K recommendations. Actually, this feedback is used to provide a reward for optimizing this whole framework. Okay, and this is all for the adversarial attack in recommender systems. And before